All right, so we're going to talk about PreVice, a tool to statically detect hooking capabilities in machine code.
Cool. Hey, I'm Derek. Pardon me. I'm recovering from illness. PreVice is a, how's the sound? Is that loud? We good? Okay. PreVice is a standalone static analyzer, and it detects a hooking code, a hooking capability in Windows binaries. The name is, of course, a salute to Jamie Butler and Greg Hoglin's 2004 work, Vice. You might remember those of you who've been in the industry long enough might remember the talk captioned, Vice, Catch the Hookers. They endeavored to detect hooking after it had happened, like hooks that were already installed in the system. We aim to detect hooking before it happens, a hooking capability. Please work. PowerPoint. Okay, so I'm going to start off by just showing you it in action, and then we'll talk about what we saw.
We have slides again.
I think
Oh, heck.
we have dual monitor.
Do I need to drag this? Hey. Okay, so I'm just going to run this on a semi-random sample. It performs the analysis, and we have our output. What it detected, where in the code, in the sample that it detected it, and a general hint on what it detected. So pretty much the rest of this talk will be explaining the underpinnings of this and kind of, the motivation and how we accomplish this, and then some interesting things that we found when we used it. There we are. So for anybody, beg your pardon?
Yeah.
We good? Okay. For anybody who's not too familiar with this concept of hooking, you can give just a quick breezy introduction. Hooking as we're defining it here, is unsanctioned interception of execution. That differs from sanctioned interception of execution in that this is not like an operating system defined callback or notification routine, something like that. Unsanctioned here means unofficial, which means there is no contract, there's no interface, there are a few guarantees. And so because of that, and also just programmer laziness, convenience ends up being a major component of hooking. They want something, the hookers want something that is easy to locate, as well-defined an interface as possible, as many guarantees as you can have without it being sanctioned by the operating system. Stable, they don't want to have to rewrite it for every single version. They might not even have access to the versions that their software is going to be running against. And there's also certain kind of like contextual needs that they have. For instance, they need their code that's intercepting execution to run in a certain context, when certain data is in scope, when they have the opportunity to abort execution if they don't like what's happening, or to change parameters, something like that. It's very useful. It's just used pervasively. Microsoft uses it in their application compatibility. shims, rootkits use it, obviously. Security software, I don't know if you can write a security product without using some form of hooking, for better and worse. These are the techniques that we're most interested in for the purposes of this talk. The last one is just kind of like a miscellaneous, none of the above. I'll get to that. This is kind of like illustrations of these concepts. Detours is my personal favorite, and that's kind of jargony. I don't know what the official text, if there were a textbook of hooking, I don't know what they would call this, but I'm gonna call it detours and code hooking kind of interchangeably. The idea is that there's a function you wanna hook, and you change the code. You change the code in a fairly standard, kind of well-defined way. You wanna intercept it before anything has happened, do your stuff, and then execute the original. Well, you just overwrote some of the code. You have to kind of replay the code that you overwrote and give the function a chance to execute as intended. If you're overriding the prologue and then you don't do the prologue before you pass back control, it's running, like you've violated its assumptions, and it's going to crash. The interesting thing about this one is that there's just one copy of the function, and you're hooking it for everybody who's calling it in that process. Export table, this is kind of a misleading illustration. I'll explain. So libraries have export tables that list the functions they expose. If you change that export table, you can cause people who subsequently look up functions that are exported by the library to get a different function instead, to call your function instead of the library's function. Now, the misleading part is that you don't call exports through the export table every single time. You just look them up once, and then you keep that pointer. So if modules are already loaded, and then you go change the export table, that's not going to affect what they call. They're still calling the old one. But we'll actually see a sample that addresses that much later on. Import tables are more interesting because pretty much every single time that an import's called, it's being called through the import table. And the import table is specific to the caller. So if you wanted to hook one caller's kind of view of the world, if you wanted to intercept one caller's call to a function and not another's, then you can do that by hooking their import table and not theirs. Meanwhile, in the kernel, there's a lot of interesting hooking, and made all the more interesting because it's in the kernel and it's just exciting. So the first one I want to talk about is there are a bunch of MSRs, model-specific registers, and they're all indexed by number. They're all well-defined numbers. There's one, what is it, like CO080, something like that, 82, that contains a code pointer. And if you change that MSR, if you're in ring 0 and you do the right MSR instruction, you can change what's in that MSR. And then, so in the case of syscall and sysenter, the instruction pointer gets loaded out of that MSR. When the syscall happens, execution goes to whatever's in the MSR. Change the MSR, execution comes to you. I don't think anybody does that, because can you imagine the overhead of intercepting every single system call? Like, the kernel's already pretty finely tuned to minimize that overhead. But it's possible. Interrupt descriptor table, kind of similar. IDT is a bunch of descriptors, one per interrupt, 0 to 255. They're kind of deprecated in a way. Like, used to be Windows, int2e was how you made syscalls, before there was a syscall instruction. So if you went and hooked the int2e descriptor, then the same thing, you're getting in the middle of all the syscalls. Also not that common, but noteworthy. System service descriptor table. Now this is pretty common. Anybody who used to hang out on rootkit.com, I'm sure knows all about the SSDT. So when you do int2e, when you do a syscall, execution's going to the system call dispatcher in the Windows kernel. This is all Windows specific. Sorry for anybody who doesn't like Windows or doesn't go there much. It's all Windows this afternoon. So the dispatcher looks up, okay, you're passing in a call number, a system call number in EAX. You want to do call 123. Well, it's going to go and look up item 123 in the SSDT, and then that's where the call is going to go. Change the SSDT, you can send execution to you for certain syscalls. Like if you want to intercept open file, you can change the entry for open file, and then it's coming to you, and all the others continue to go to wherever they were going. None of the above. There are many other things you could do that could constitute hooking that we're just not really going to talk about today. You could change the window proc for a window by doing like set window long. You can hook vtables. That's a really good one, and we should probably look into that a lot more. For COM objects or just for like object-oriented objects generally. And then if you know a specific piece of code that you want to patch, you can always just go patch the code. Like I think there are some people who patch LDRP load DLL, or maybe like LDR load DLL's call to it, by just going and patching the call instruction in the middle of the function. You're taking on more assumptions at that point. You have kind of fewer guarantees, but it's just an example. Ultimately, hooking is limited only by your imagination. Let's see. Okay, so that's hooking. Now we're going to talk about how to detect it. Of course, anytime you want to solve a problem, I think it's usually beneficial to ask first, what have other people done? So obviously, we start with Vice. If there's something before Vice, like anything serious before Vice, I don't know about it. I tried to be fairly comprehensive, but Vice inspired a whole proliferation of things that also look for already installed hooks in memory. Yeah, they're all listed up here in roughly chronological order. I didn't list Gmer. I couldn't find good information about how it works. I'm sure there are others I missed. I apologize to their authors. But there's only so much room on the slide. So yeah, Vice, I think, would pretty much check for import hooks and export hooks. And yeah, it's been a while, so I might not be giving it due treatment. But it looks what was, I believe, either what was on disk, or it looks at what's in memory just for suspiciousness. Hook Scout is an interesting one. I think they were trying to do kind of like the theoretically near ideal, kind of like end result of trying to find hook points. They was it Hook Scout or Hook Finder? I believe that they were looking for pretty much anything that you could hook, like trying to find function pointers all throughout the kernel where that you could change in order to intercept execution, instead of just the most obvious ones that people think about, imports and exports. Volatility plugins for looking at memory dumps for evidence of hooking. But this is all well after the fact. The hooks have already been there, and somebody's gotten suspicious enough to run one of these tools. Dynamic analysis, detonation as some people call it. You have a sample you're suspicious of, you run it, and then you, on this instrumented system or in a sandbox, and you're watching to see if it does hook-like behaviors, if it is changing things that maybe it shouldn't be. Hook Finder is a really interesting one, also by, I believe, Dawn Song's team at Berkeley. If their name turns up whenever you're searching for your idea to see if it's been done before, you should probably just go find another idea, because they always do really cool work. So I didn't see Hook Finder until after we'd already gotten accepted and kind of, had been well into the work. So I was kind of nervous. I was afraid they had already done what we did, but turns out it's full system emulation. They're doing some interesting, I think they called it impact instead of taint. It's interesting. It's worth a read, and there's a link for whenever we put these slides up. But yeah, it doesn't overlap too much with what we're talking about here today. I thought this other one was interesting. They have boot code that they're curious about, so they just emulate it, and then they watch for, does it modify the interrupt vector table. Emulation makes sense for that, because I think like boot code is going to be fairly linear. There probably won't be, the system's in a very primitive state, so there's not going to be a lot of initial conditions that would cause it to take different branches. It'll probably just do one thing every time you emulate it, if your emulator's good. This was the closest that I found, looking for prior art. Don't laugh. They are using IDA. Like a lot of academic solutions, they are using IDA, and they were just essentially grepping it with a complicated Perl script and a bunch of regular expressions, but it was really kind of like erudite choices of regular expressions. Like reading their white paper especially, they know what they're doing, and they just took this kind of like least effort path to do it. Like, that's pretty solid. There aren't too many ways short of like emitting or modifying code at runtime that you could disguise your access to CR0. So that's a pretty cool one. It was, however, only for kernel stuff. And also, this is only suggestive. Like turning off the write protect bit so you can write to read-only memory is very suggestive, but it's still only suggestive. It doesn't positively say, here's the hooking, here's what's happening. So we need something more powerful. Okay, so yeah, basically this is the goal. We want to know if a sample can hook, if it has the capability in it, without running it. We want to know how it hooks, what technique, export, import, et cetera. And we'd like to know what it hooks. And most of all, we want to be able to tell the researcher where to go in the code to look at it some more. Because ultimately, this is I mean, there are lots of interesting things that you could do with this kind of information, but in this context, we just want to give a tip to a researcher. And obviously, we want to reduce false positives because we're talking about giving tips to researchers. If we give them a bunch of bogus information, then they're not going to use this anymore. So this is kind of how it would look with those techniques that I listed earlier. For Detours hooks, we'd like to know what function that they're hooking if we can figure it out, and what bytes they're writing there. For instance, if they're writing an E9, that means they're doing a jump, and that means certain things. If they're, oh yeah, I guess that's the best example. If they're just writing a C3, that's a return instruction, and that means they kind of just want the function to not do anything anymore. And we might see some examples of that. If they're hooking exports, what export? Import, what import? If they're hooking syscall, sysenter, MSR, about all we can tell you is which MSR they're changing. Are they doing syscalls, 64-bit syscalls, or sysenter? Probably not doing sysenter because nobody uses it. Probably syscall. IDT, same thing. It's almost certainly going to be 2E, unless they want to intercept breakpoints or IRQs or something. SSDT, system call number, that's not eminently informative because the system call numbers change per version of Windows, but they're fairly stable, and if you have a system call number, you can probably go look it up. So, obviously we're here to talk about a solution to these problems, and this is what our solution, in a nutshell, aims to do. For all these different techniques, we want to detect. Ultimately, it all comes down to one pivotal instruction. When they're changing that MSR, when they're writing to that memory, yeah, that's basically it. So there's that one instruction, but you can't write a Yara rule for that instruction because there's so much contextual. There's the operands and which choice of register they're writing to, et cetera, et cetera. There's a whole lot of information you have to know leading up to that one instruction to say, I think with high confidence, that's what this instruction's doing. And that's where we transition to static analysis. This is our weapon of choice in solving this problem. Here, we're defining static analysis as just abstracting the meaning of code. You got a pile of bytes, you got a pile of instructions. What do they do? How do you express that in a meaningful way? Because we have this purpose, we have a goal that we want to achieve, kind of an endpoint to get to. That kind of guides what abstractions, what information is useful to us. So, kind of like the typical stack of abstractions, you got bytes to instructions clumped together into basic blocks into graphs, and then also functions as a scope is kind of like a subunit of the graph. Typically makes sense. Now, to get a little bit theoretical or philosophical, you can imagine at any instant, you have the state of the system. You got memory, you got registers, et cetera. I guess as we heard in the Windows Defender talk this morning, there's a whole lot of state. If you want to consider the state of the disk or et cetera, it could be pretty expansive. A single state is really large. If you want to consider the program as a series or execution as a series of state transformations, it's impossibly vast. Unless the program is doing exactly one thing on exactly one set of initial conditions, it just rapidly proliferates into an unmanageable number of states. I like to think about static analysis as kind of parameterizing the state. If you had a function that gives you state, what is the parameter to that function? For emulation, for execution, that parameter is time. But the time is kind of unbounded. I guess that's where people would invoke the halting problem. If you parameterize it as a function of space, in other words, of position, you can say, at this point in the code, this is what we know about the state. Anytime that execution reaches that position in the code, that's a lot more bounded. It's also very imperfect. You can think loops or recursive, any way that execution could reach one point in the code with two very different states, and there are a lot of ways that could happen. But this is all an approximation because of this unmanageable state space. You're approximating, you're compromising, you're doing things to try and minimize the runtime and then maximize utility of what you're doing. And that's what I like about this problem of detecting hooking is that it's fairly narrow because we're trying to find that one instruction that's doing the one interesting thing. It's not too far removed from the machine code. Of course, there are, well, as I was just saying, there are challenges to this. We want it to run quickly. We don't, we really don't want it to be slower than detonation or emulation. And there are ways that you absolutely could make that happen if you weren't careful. So again, more compromises and more kind of like judicious choice of algorithms. Also don't want memory to just go crazy. And we do want to be accurate, of course. In the static analysis context, you're going to have like unknown initial conditions. You're going to have indeterminism creeping in from outside, and trying to manage that whenever possible. Obviously, sometimes emulation, just in a targeted way, is the tool of choice. But you got to keep that under control also, because that is a function of time. And yeah, again, we want to minimize false positives. So that's enough out of me. I'm going to hand off to Andy to give you the good stuff.
All right, so I am still Andy, and I'm going to talk about in a little more detail PreVice, which is the tool and algorithms we've put together that actually lead us to that confident determination of this is the instruction that does hooking and what that hooking entails, what is being hooked, what was written, and what the change is. So when you're looking at any executable, you start with a bunch of bytes. We're focused on Windows 32 and 64-bit native code, mostly just because that happens to be the domain that we're most interested in at the moment. I mean, if we're still analyzing x86 code, there's no reason it couldn't work on other formats, right? That's just a question of making the adapter from format to our tool. We're focused on portable executables. The actual executable code, any data contained in that executable, and any metadata describing it. Important stuff being the machine architecture, which indicates to the Windows loader and to us, is this going to be 32 64-bit code, what the permissions on the sections are, so we can be pretty confident that stuff in a data section is not going to be treated like code as long as several other assumptions hold, which sometimes don't. And imports are really important as well, because you need to know if there's a call to something through import table, as Derek was talking about, what does this program expect to be there? Once we have that information, we have to go through and find the actual bytes of code. So TLS callbacks, if they're present, are going to be executed before the entry point of the program. If the entry point is present, then the entry point is going to be executed, and exports are probably going to be code, but of course you can export variables as well. So once you have a bunch of bytes, we're going to have to reassemble that into something more useful, the instructions. In x86, 32, 64-bit, you have a sequence of optional prefixes. You have the actual opcode itself. Depending on the opcode, sometimes you have a byte afterwards. Post byte describes the operands a little more. Sometimes you have a displacement, sometimes you have an immediate. Really, the presence of any of those is a function of the opcode, though. So simple example being E9 for a jump, right? You have an E9 and then 4 bytes of address, like relative distance that you're going to go. Another one that we're going to actually see a little bit later is like move register some immediate. So you have a prefix to talk about the extended register RAX instead of the EAX. You have the immediate that comes afterwards. And same for, and following by the jump to the immediate you just loaded. So jumping to the register RAX that you just loaded an immediate into for your hook, that's going to be a separate instruction afterwards. And then, of course, there's rip relative jumps, which you see for some other code. And there's a lot of instruction-specific logic. Some approaches for this are, of course, lifting your instruction-specific logic for your target architecture to NIL. Regardless of the approach you're taking, you still have a ridiculous number of types of instructions. We have a 500 case something switch statement in there somewhere. And that's not including some of the variants. So for the F6 opcode, that's one of a handful of instructions determined by one of the bytes, one of the fields in the byte describing the operands. And it's important for us to know what reads and writes are conducted by executing this instruction. So if you compare ESI, EDI, that is the opcode 39 and the post byte FE, Okay, so you're going to read the register ESI, you're going to write to the register EDI, and, reading ESI, reading EDI, and you're going to write to the flags. Depending on how you model the flags, it may be sufficient to assume that there are no modifications in registers you care about, if you're looking at only the general purpose registers, which for some subsets of the problem is what we're doing. If you have a displacement, so you're doing something relative to where a pointer points in memory, like the exchange EAX, I don't have a laser pointer. I'm going to borrow a laser pointer. Yeah. So in the exchange EAX EBP case, we have a displacement of 4 indicated by the byte 4, and the 8745 indicate the exchange EAX and EBP relative to memory. And of course, in some other cases, as this is all conditional on what the opcode itself is, move ECX is the B9 opcode, and the immediate 1 is indicated by the 4-byte immediate afterwards. So going from instructions forward, the next kind of convenient unit of abstraction is a basic block, which is a sequence of consecutive instructions. I think a lot of us are familiar with those, but it's an important place to stop and think, okay, if we're going to try summarizing these states as a function of our position in the code, we can come to a conclusion about the state before and after a basic block, as long as we're assuming there's no surprising control flow, like there's no fault that happens. And that's an assumption that holds pretty well most of the time. If you try to model faults as possibly breaking a basic block, the program explodes in complexity and it just really ends up being problematic. So once you have basic blocks, those are a nice unit, a natural unit to go from basic block to a graph of how those basic blocks can flow together. So in our example here, we have JZ, which means we either conditionally jump to 4 or we conditionally jump to basic block 2. And basic block 2 is part of a loop, so we may conditionally go back to 1, modeled by the back edge in the graph, or go forward to block 3, which precedes itself to also go to block 4, where they exit. And in graphs like this, they're actually really convenient to model as even higher levels of abstraction functions. So we can talk about kind of what do these basic blocks do when taken together. Functions, of course, aren't mandatory. You can write some assembly that is absolutely miserable to read and doesn't have any kind of consistent calling convention. It's a good enough assumption for our purposes. And we really take a function to be a directed graph because control flow is by nature directed, right? And it has a single entry point. If we have multiple entry points, it turns out that we can treat that as multiple functions that happen to contain some of the same code. That's not a really large issue. And once we kind of treat this function as a box, right, the calling convention that we have to care about really is the arguments going into the function and how it returns. So there's a scope for all this analysis to be done in, and the calling convention and signature really give us a lot of information about the way we expect this to be called and how we would set the initial state for analysis. So talking about that a little bit more, like I was saying, the signature really talks about the count of arguments and their types. So if we wanted to say we know the second parameter is going to be the pointer to a PE, that's an important piece of information that we need to be able to propagate. If we're talking about the calling convention, so Windows standard call is going to be on the stack left to right, and the callee is going to clean it up. So we know when this function calls, the state of the stack should be the same. For cdecal, the caller is cleaning it up, callee cleanup, right? The function being call is going to move the stack. Callee cleanup, caller cleanup, the state's going to be the same. And then on 64-bit, we actually pass a bunch of parameters in registers, and then perhaps some on the stack as well. So it's important to really be able to infer either from assumption by being on 64-bit Windows, assumption by being on 32-bit Windows, or actually infer by analyzing the function what the calling convention is. And then, of course, in addition to all of this, we have stack local variables, which are expected to be not tampered with by subsequent calls down the call sequence or somehow preserved to be used outside the function. But of course, that can happen too if you're trying to do any kind of anti-analysis trickery. And it is really important to just highlight the assumptions you're making when you're doing this to understand where the issues will happen, and you can come back to fix them later, right? So as an example, if you're going to do syscall hooking, right, like Derek was talking about, you're going to want to set a value into the L star MSR. So you're going to write a new address into it. And the way you modify MSRs on x86 machines is you use the WR-MSR instruction. So what we're doing in this example is, okay, we're going to take some hook address, the place we want control flow to go, and we're going to take the low 32 bits, put those in EAX. We're going to take the higher 32 bits, put those in EDX, and put the actual number for the L star MSR in ECX, and kind of like make a call. You know, we're going to issue the MSR instruction, which is going to put EAX in the low 32 of the MSR, and EAX in the low 32, EDX in the high 32, and now you have taken over L star. You have taken over syscall. And of course, if you wanted to look for it, you could write a YAR rule for B8, 4 bytes, BA, 4 bytes, B9, 4 bytes, 0F30. That could work as a YAR rule, but as a more complex example, like it's no longer clear at this MSR, do you actually care about this MSR? So if we want to be a little more careful, we can look more specifically at the values as they're being processed. So EBX is started off with 0x0000 ADH. All right. And subsequent places where EBX, ECX are used, ECX is stored here. ECX is also stored here. EBX is read as well. EBX is read and stored to ECX. RBX is read and stored to ECX. And then eventually there's a syscall, there's a WR-MSR at the end. So looking at those values in particular, all right, so in this first case, we know EBX is going to be C80. And we can propagate that information forward and figure out for all cases, now we know what ECX is. So here, ECX is C80, and you're going to read that MSR. Here, C81, read the MSR. C82, that's actually the one of interest, and you're going to read that out, and we're actually going to load it back up again and then write to the MSR. So it's in the context of a single basic block, this is tractable, right? You can just emulate the basic block and see the values you know. And of course, say this is the hook that you want to write. So this is the value, and then you shift that right, and now you know the parameters for WR-MSR. You know the MSR is going to be written, and you know EAX and EDX for the hook that's going to be written. Now, as we're doing this, and we're talking about emulation, there's a couple of cases where we need to do kind of special logic. And a lot of cases, we just know the inputs. We know 1 plus 2 is 3, right? But 1 plus something we don't know, we just don't know the result. And we know XOR if we know both inputs. If one input's unknown, we, again, don't know. So we can do that, define that for many arithmetic operations. If the parameters are known, we know what the result is. In some cases, arithmetic on undetermined operations is actually important as well. So sub-register by itself is thing minus itself. It's going to be 0. We can determine that in kind of a modified execution context, modified emulation context even. We can make that determination without knowing the register in question. We just know what the result is going to be. Multiplication by 0, less common, but technically we know the results. XOR by itself, again, really common way of getting 0. And by 0, again, we know the result. And by virtue of knowing some registers, we may be able to be more confident about others. So we look at the first instruction, we know C80, and we know RCX is going to be the result of the thing we had before, which we now know, C80, plus 1, and we take the low 32, and then store that into ECX. So we apply this logic to the program at hand, the basic block in hand, and determine any results if we happen to know them. So the state of the program at the first basic block, we don't really know many of the registers. We know RBX because in the first instruction here, you're moving the constant into RBX. We know RIP. So we go forward and we go to the next right and look at LEA, RAX, RIP relative. Well, we know RIP, we know RBX, and from those we know we can come to a conclusion about RAX. Same case for ECX as a destination. We can come to a conclusion about ECX as a function of RBX plus 2. So we know RBX plus 2, C blah, 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 2. And again, for when we're getting the high and low D word of the hook function, we can come to a conclusion about that by, again, kind of emulating the instructions at hand. Even in this case, if we don't know the values, we can still talk about, we don't know the concrete values, we can still talk about kind of symbolically, REX hasn't been written to, so we can just give that kind of a nice name. So it's REX something. Again, RCX wasn't written through the sequence of instructions, so we can just call it RCX that we didn't know. And same for RDX. And eventually we do come to a conclusion about the concrete value, and that's more concrete value we can use in going forward. Taken to an extreme, this is theoretically a more powerful way to process the program, but it comes at a computational cost, and we're trying to be quick, right? We don't want to be slower than just running the program and seeing what it does. In this particular case, there's no control flow. It's very linear, so taking a full symbolic execution approach is tractable. Now, if we want to look at like what code that applies a hook actually looks like, it's going to probably look something a bit like this if you're taking the overwrite some code approach. So for anyone not entirely familiar with the Windows APIs, get module handle A gets you a handle to the base of this module of memory, kernel 32. You're going to pass that to get proc address and say, okay, well, in the module that I just said, look up the function, find first file A, and give me that address. So PB is now the pointer to the function, sorry, PB is the pointer to the function find first file A in kernel 32. And they're going to change that to be executable and read write, and then just start modifying bytes there. So they're going to write their E9 for a hook, and then the actual value they put in the 4 bytes afterwards are going to be the relative adjustment to that hook location. And that turns into this machine code, which is relatively straightforward in this case. You push your parameter, make your call. This is 32-bit, assuming here. So you push your parameter, make your call. This is a pointer to kernel 32.dll. Push your pointer, push your handle, make your call. So this is a pointer to the find first file A function. And so on. So you end up calling virtual protect, and here's your write for the E9. EDI here coming from EDI right after get proc address. So we just took the address, sorted to EDI, and wrote to it. So the corresponding lines in the original code kind of correspond to these instructions are kind of the hook relevant ones, right? So these two do the writing, but how can we determine that through static analysis? And the way we're approaching that is by propagating type information about the registers or about the values that we're tracking. So we have kind of interfaces and conventions described by the operating system, maybe by the CPU, by any kind of, well, many means. One of the other ones that is kind of interesting is in 32/64-bit, you have the FSGS registers that will give you a pointer to the TEB, which you can walk to the PEB, walk to the loader data list, which is an alternate way of getting to module handles. So you can call get module handle A and get proc address, or you can get a module handle eventually through the loader list. And there are CPU-defined interfaces that give you well-known structures as well. So the CPU-defined interfaces, they aren't going to change per OS, which is actually pretty convenient. Now, the way those are used may change. So some OS may use sysenter versus syscall, and you need to understand that appropriately. But the underlying analysis of how the CPU works conveniently stays the same. So if we look at this code example again, and we try to propagate the types, the transition rules are kind of defined by each operation, by each instruction. So we know after get module handle A, the result of this is going to be logically a handle to some PE, which is also going to function as the base address of PE. We know get proc address is going to give you a pointer to code. So we know after this move, we can have a rule that says, okay, when you do a move, the result is going to have the same properties as the input. So you do a move, we move a code pointer to a location. This location EDI now also is a code pointer. Later on, if we can prove that EDI has not changed by this instruction, we know the right destination is a code pointer. And then a right pointer, code pointer plus some small offset is also probably still a code pointer. That's not necessarily true. Like, this could be a 1-byte function. This might write to another value. But it's an assumption we can make that holds often. And of course, if we want to look at the actual values, kind of annotated on top of the disassembly. So get module handle A returns image base. There's the image base as you push it, code pointer, and we're actually writing to the code pointer now. And yeah. So it's really important to be able to propagate types because we actually can go a step further and say not just that there's a write to the code pointer, but which code pointer was written to. We can actually say, okay, pointer to kernel32.dll. So we know that's going to, too many slides. So we know that the image base that you're going to push is actually the image base of kernel32 in particular. And the function you're looking up is find first file A in particular, which means afterwards we can say, get proc just return me a pointer to kernel32's find first file A. And of course, now we can be more specific and say, we know this code is going to patch find first file A rather than patch some code somewhere. Now, for propagation of type information across basic blocks, we need to be a little bit more careful because what happens when we have two code paths that come back together? It becomes tricky. And this is actually taking a page out of the compiler theory book. And there's a couple of reverse engineering tools that also have taken up static single assignment as a translation. It's actually very nice to see. So what we end up doing is we come up with a new name for any time a variable is modified. So when we do a move, right, we're writing to EAX, so EAX is now like EAX iteration 1, version 1. Now we write to EAX again, EAX is version 2. But we know that the EAX that was read in the memory operand was the previous version before the instruction. So the result of this instruction, this move, is going to be, we can call it EAX2, and it's the result of reading memory at EBX EAX1 78. And then we add these together. Addition may be a small tweak, but in the most strict sense, it is a replacement of the value. So we say EAX3 and so on. So we actually have a little table, as the program proceeds, as this basic block actually proceeds, what the numbers look like. And of course, this is walking some PE headers. So you get ELFA new, and you walk through the PE headers to get exports, I think. My brain's kind of out of it. Now, at control flow junctions, when control flow can split, you don't really know what this is at the return. So say you're going to check for 32 64-bit and then read the right offset for the appropriate data directory. When we come back together and add the RVA to base address, EBX base address here, we don't really know which EAX this must be. So when you're working with static single assignment, when control flow can come back together, you have this little phi function, which says, okay, the result in EAX4 is one of EAX2 or EAX3, depending on which path brought you here. And then we can go forward with whatever information we know about EAX4 at that point, add EBX, EAX5, and so on. So phi functions make a really convenient point to do some constant propagation as well. So if we know that there are going to be two concrete values, or multiple concrete values, we can take kind of the most minimal set of information we still know. So if we know in bits here, or decimal works as well. But if we know that the second digit is 0 in all of these cases, we know in the result it's still going to be 0 regardless of which path. And that might be interesting when you're looking at, say, bit flags. And we can do type propagation of phi functions as well. So in the previous slide, we know the type of thing at EAX is going to be the same across both paths. And we can, after the phi function, decide it's the same logical piece, even though we don't know where exactly it is. So some other examples, if you want to be kind of assumption-y, phi of something that you know is an image base and something you don't know about, you can just assume it's probably going to be an image base. Phi of something we know to be a code pointer and an RVA probably isn't, because that's phi of a virtual address and a relative virtual address. So you don't really know what that is anymore. So kind of overview of that again. We start off with a bunch of bytes. We really just need to start working with the bytes, right? So we parse some headers, we get entry point, we get some text, we know that that's read execute. we can go start disassembling code at the entry point. We then can read imports, understand imports, and turn that into a nice graph, and proceed to do more analysis on it. So we go from graph to static single assignment, and we actually propagate types through it. So get module handle gives you image base, and we store the image base somewhere else, get the PE header RVA, and do our thing, and get the imports. And of course, there's even if you just want to focus on hooking specific information, there's still a lot of types to at least learn about and propagate. So the MSR 176, syscenter handler, C81, syscall handler, C82, syscall handler. And there's a bunch of ways that you can get the image base for a module. So you can get module handle A with an actual string, 0 for yourself, W for the module you passed, and so on. Of course, the get module handle EAX, the library EAX, get proc address. NT query information process is interesting because that's an alternate way of getting to the PEB, which would usually be FS relative, GS relative, walk through the tab, go to the PEB. And the list just goes on. In the PEB case, all right, so you have a pointer to the thread environment block, and at offset 18 is going to, or 30 and 64-bit, it's going to be an offset to itself. At 30/60, it's going to be a pointer to the process environment block. In the process environment block, you've got a pointer to yourself. That's great. And if you walk through all of this, you actually get to a list of other loaded modules in the process. So we still want to be able to walk through that and understand when code is going to be enumerating loaded modules. And in the context of a PE, again, there's a bunch of rules that you want to have to understand how dereferences with certain offsets transition kind of input knowledge to output knowledge. So image base plus 3C, that's the offset of the PE headers in that module. That plus the image base, again, gives you the actual address of the PE headers, and it just goes on. What gets interesting is you start walking through imports, and the import descriptors have their own structure. So we need to understand the structure of structures that structures point to. And it gets a little bit hairy. And of course, when we're looking at exports, you're going to have a list of RVAs to exports, and the RVA plus image base is going to be a pointer to code. So if you're going to modify the export RVA, then you're now hooking the exported function. You're replacing control flow to the function that gets looked up to whatever you describe. And same deal for imports. If you modify the imported function, then when the imported function is called, again, you have taken over control of the function. So at this point, we have information that should be enough to describe most code hooking pursuant to the assumption that we've made. We can identify writes to code pointers, however you happen to get to them, by going through the tab to the PEB, to the loaded module list, to the actual modules, by walking through the module for the export directory, by walking through for the import table. The simpler cases like writing to syscenter MSRs, writing to the IDT, writing to SSDT. And of course, there's plenty of other ways to do hooking, right? So we'd end up wanting to extend this list to maybe vtables as well in the future. And with that, we can actually talk about what we found, and I'm going to hand that off to Claudio.
Thank you, Andy. So let's go. So to recap a little bit, we started from bytes. We discovered the code. We interpreted the code as instructions. Then the instructions, we built basic blocks. From basic blocks, we created functions. We used targeted emulation using partial data because we start from a state that is undefined at the point of emulation. Then we moved on to symbolic execution, and using that, we got to this kind of results. So we have a very large corpus of millions of files, and we run this tool that we put together over a subset of, I think, 3 million samples. And we come up with some goodies here. So the first one is called Moneylord, and it's very easy. You can see that ESI contains the free console address, and what it does is just put a C3 there, which means it's a return. So whenever you call this, after this hook is in place, of course use virtual protect to assign read, write, or even execute protection. So then you write it, and it means that whenever you call this function, it doesn't do anything. So what's the benefit of that? And like the benefit, it's huge because the program that created this console frees it, but actually nothing happens. So the console exists, and somebody can attach to it using the process ID where to which the console was assigned. So that's a good way of hiding, being stealthy. And what is more in Lord, I think there is here text that it's put onto the console. So they want my money, they have to come to me then. So let's go next. So these are Easter eggs. This is it's targeting the ZW open process, and it's a very easy hook, like a jump, and the value is in EBX. Of course, there are some protection that have been applied that are skipped from this slide, but it's just jump to the relative address that was to the address. Actually, this is 32-bit to the address that was placed in either EBX or ESI. So this is something that Eddie can explain. Yeah. I can only think that when you load it in IDA, you get a PDB request that points you to a certain site, which I didn't click, even if I was on a protected VMware.
Yeah, so that sample in particular is one of my favorites because it's from some anti-cheat vendor or something. They're hooking open process, so you can't attach. But the debug directory actually is just a bit.ly link to this comic. And if you're out there, the hit you got from Southern California was me getting your image.
Okay, so this firstly was called sinful behavior because somebody is getting the address of EX allocate pool with tag, calls it, and then overrides it with something. It's like, okay, what do you want to do? But next, if you look deeper into that, you can see that you have a JB at a certain address, and then followed by NOPS, and then you have a jump not below, which actually it's a unconditional jump. So what you see here, the three instructions down, the EDI when it's overwritten with the value of ESA is not going to execute. So actually nothing happens. So anti-disassembly can trick you when you do this kind of static analysis. So we're trying to mitigate this by understanding more about anti-disassembly tricks and implementing. Okay. So next, you have the kernel user KE user mode callback put in an ESC, and you see a lot of moves from a certain address. So it's actually overwriting the ESI, like first, second, third, actually pretty much everything. I don't see it still there, so 16 bytes. But instead of using move SB, they chose to go byte by byte. I don't know why, but maybe they like to write more code than it can. And then to follow up, they're doing some comparisons with the values there to see if the patch was applied. I don't know why they're not comparing those 6 bytes. Maybe they're random, like they differ depending on the address that you're hooking. But that's what it is. Next, we have hooking of the NT-map view of section. They're nice enough to save the original 5 bytes of the beginning of the section. Then you have the hook, which is at 1274A. They compute the displacement, and they are accounting for the jump instruction, which is 5 bytes long. And then they're writing the hook, and then the EAX, that is the value of the displacement of the RV of the EAX. Actually, it is the displacement of the hook. And the funny thing is, when you look into the hook, the function hooked is NT-map view of section, which load library calls it. So in the hook, you can see that there are checks for different path of OLE32 DLL. So maybe whenever you try to load OLE32 DLL, is not loading the one that it's in system32. It's going to load aside the DLL and bypassing the what's the name? The order of loading DLLs. So this is more interesting. It's NTOS kernel patching. So it's patching the anti-query system information. As you can see, it's putting the 16 bytes from XMM0 into RX, and then in the 17th byte, it's the ret. And let's go. I think we're out of time. Is it correct? So I'll go fast through this. In the XMM0 contains the 16 bytes that are presenting in the first 3 lines. So if you are looking at it in Little Endian, so you have a knob, you have a 50, which is it's a push RX, and then you go 48 B8, and then followed by 8 bytes, which is move REX 8-byte number, and then you have 48 87 04 24, which stands for exchange top of the stack with RX, and then return. So actually, this is the thing that's happening. So this is the hook that overrides the beginning of let me see what's the function. I forgot about it. Yeah, it's anti-query system information. And while looking at it, Andy saw some interesting things related to the patch card. I think they're trying to disable it, and there are some print information to get the XOR key out. If you have any more details about that?
Yeah, there's nothing really, we didn't spend enough time to be confident that's disabling patch guard, but looking for immediates in this code and looking for some of the debug strings, I'm pretty confident it came from a project on GitHub that professes to disable patch guard, which is kind of neat, like actually hooking 64-bit code and still working.
Okay, so since we have 3 more minutes, I can have a demo. So let me see the first one. I'll drag it on the other side. Okay.
You're going to want to drag that over to the other screen.
Yeah, I will immediately. So this is actually the sample that we looked at, the last one with the NTOS patch card. So we detected that we were able to successfully go through it. We know the image base, and we detected the following NTOS, the hooking operations that are performed on anti-query system information, PS lookup process by ID, and PS lookup thread by thread ID, and those are the RVAs to which it was detected. So now let's go and open our friend IDA. It's B. Okay. So let's go a little bit. So what we see here, like this is the first thing that you get to it and see that CR0, it's modified to remove the write protection. So you see here, it's ending with FFE, FFFFF. So you can write to it. Here is the XMM0 that was created here, and it's exactly the ones that I mentioned. And then the end in C3, the return. And then here, the device, the write protect, it's turned back one after you're done with the hook. And the same thing happens for process ID, lookup process by process ID, and the same type of patching happened, and also the lookup process by process ID. And and there is also the thread one. Yeah, there is thread here. So this all have been detected correctly and showing bad stuff happening through static analysis. Thank you very much.
So I think we can do a quick few questions because the next speakers need to still prepare, right? Okay. Raise your hand, okay.
The question to Andy about registry set collection. Did you collect registries over each instruction or only in places of changes?
So we're identifying modifications only when the register could have been modified. Any place that the register is still read, we still look at the SSA value that is appropriate at that point in the program. I think.
Okay. And another question related to first. Did you use the function call graph to detect the value of noun addresses and registers?
So that's an extension I would like to add soon. Not at the moment. That would be a very good place to go.
More questions?
There's a hand in the back.
So you guys plan to release any of this code, or like the framework you build is quite awesome, and I would love to build on top of that. But yeah, so it's quite a lot of work put on the analysis framework itself. So do you plan to release it?
I want to. I would like to. I hope so.
Hope so.
Please come talk to us afterwards, though.
Okay, sure.
Thanks.
Thank you.